Good day everyone. Welcome to my channel where physics learning is highly possible and important to the author. Aside from finding micro solutions for problem of food shortage even in the city through urban gardening, he's also trying to make learning physics easier to everyone despite of the present condition where face-to-face classes are not allowed, and teaching and learning could only be safely possible through online or virtual classes only. Today in this session, a virtual experiment about liquid pressure will be performed. I hope that you will attain the objectives of this experiment and learn the topic through the experiment. The objective of this virtual experiment to determine how liquid pressure varies with the depth of the liquid, direction taken in the liquid, density of the liquid, cross-section of the containing vessel. To attain these objectives, the following materials will be used: the manometer, the big and small jars which are now calibrated. For the liquids, we will be using kerosene, glycerin, and of course the water. The setup showing the manometer, the glass container, and the water. The theory behind this experiment to help us understand what will be happening and what we'll be observing in this experiment. When a fluid is confined, it exerts a force F which is perpendicular to the walls of the container, whose area is A. The pressure P, which is exerted on the walls, is defined as the force per unit area. The equation then is presented as pressure is equal to the force divided by the area. The SI unit of pressure is the Pascal, symbol PA, or 1 Newton per square meter. Other units are dyne per square centimeter and pound per square inch in CGS and the FPS system, respectively. In a cylindrical water tank, the pressure is exerted at all points within the water. The pressure is always normal to the surface of the wall and is independent of the shape of the container. This type of pressure, which is caused by the weight of the liquid, is called hydrostatic pressure. This pressure is dependent upon the height, y, of the liquid and its weight density. The formula is shown as pressure is equal to density, acceleration due to gravity, and height. The mass density of a liquid is practically constant since liquids are nearly incompressible, while for gases, the density is comparatively small and the difference in pressure between 2 points is negligible if the change in elevation delta y is not very great. Due to its compressibility, the density of gases cannot be considered constant. The difference between an unknown pressure and the atmospheric pressure is called gauge pressure, and the true pressure is called absolute pressure. The absolute pressure is equal to the atmospheric pressure plus the gauge pressure. In the case of liquids, the gauge pressure is the same as the liquid pressure. The equation is given by absolute pressure is equal to the sum of atmospheric pressure and the product of density, acceleration due to gravity, and the depth of the liquid. The procedure to follow in this experiment: first, set the manometer for use. Note down the initial readings of the liquid levels. OP for open arm and OQ for the closed arm, and record together with the difference OP minus OQ. This figure shows the setup, the manometer, the calibrated container, and the liquid. The height OQ and OP. For the first part of the experiment, the variation of liquid pressure with the depth. Calibrate the smaller jar by 3 cm with the 0 mark placed below the mouth of the jar with provision for the rise in the liquid as the probe is dipped. Fill the jar with water up to the 0 mark. While keeping an eye on the water level in the manometer, dip the probe of the manometer upside down into the jar of water so that its tip can be placed at 3 cm from the surface of the liquid. At each depth, read and record the height, OP and OQ. Tabulate as shown in Table A and complete the table. Now for the second part of the experiment, variation of liquid pressure with direction taken in the liquid. Repeat procedure A with the probe of the manometer directed sideways to the right. Repeat procedure A with the probe of the manometer directed to the left. Tabulate the data in Table B and complete the table. For the third part, variation of liquid pressure with density. Repeat procedure A using kerosene, then glycerin. Tabulate the data in Table C and complete the table. For the last part of the experiment, variation of liquid pressure with cross-sectional area. Repeat procedure A using a jar of bigger cross-section. And tabulate the data in Table D and complete the table. Now, let's have a video clip on how the experiment will be performed. So, this shows the setup. On the first part, variation of liquid with pressure variation of liquid pressure with depth. Now observe how the experiment is performed. So the probe is dipped first at 0 and then at 3 cm, at 6 cm depth, and at 9 cm depth. So at each position, you have to read the column of water, OQ for the closed arm, and OP for the open arm, and record. So you will be collecting the data on the data collection part in this video. Now the second part. Variation of liquid pressure with direction taken in the liquid. First, we'll have the right direction. Note that the probe is bent to the right. Positioned at 0. And at 3 cm mark, note and observe the column of water on the manometer. So at 6 cm, at 9 cm mark. Now, to the left. So variation of liquid pressure with direction taken in the liquid, and then the direction is to the left. At 0 cm mark, and then dipped to 3 centimeter mark, at 6 centimeter mark, and at 9 centimeter mark. Note how the height of the column of water changed in the manometer. Now part C, variation of liquid pressure with density. For this time, let's have the kerosene. At 0 centimeter mark, at 3 centimeter mark, now dip to 6 centimeter mark. So this time the probe is again positioned upside down. And at 9 centimeter mark. Then for the glycerin, now at 0 centimeter mark, or at the top of the liquid, at 3 centimeter, at 6 centimeter mark, at 9 centimeter mark. Now for the last part, variation of liquid pressure with cross-sectional area. Now this time we are using a bigger jar, so with a bigger cross-section. So the probe is positioned upside down, similar or just the same with the smaller jar. Now at 0 centimeter mark, at 3 centimeter mark, at 6 centimeter mark, and at 9 centimeter mark. So in this experiment, at each position, you're going to measure the height of the closed arm and the height of the open arm. But first, you have to take the initial position. So, in the next slides, data collection will start. So be ready with your activity sheets, your pen or pencil, paper, and your calculator. So you may pause the video if you need more time for reading the column of the water in the manometer. Now let's start. Here you're going to read the initial height of the column of water on the closed arm, OQ, and OP for the open arm. Okay, so this is the expanded view of the ruler in the manometer and the column of water, OQ and OP. You may pause the video if you need more time in reading. Now let's proceed. So first part of the experiment, variation of liquid pressure with depth. So at 0 centimeter mark, this is the expanded view. Again, you may pause the video if you need more time in reading the measure. At 3 centimeter mark, at 6 centimeter mark, at 9 centimeter mark, read and record on the table provided on the activity sheets for part A, variation of liquid pressure with depth. Take note, here we're using the smaller jar and the probe is positioned upside down. Now let's move to the second part of the experiment. So variation of liquid pressure with the direction taken in the liquid, and the direction is to the right. Now at 0 centimeter mark, at 3 centimeter mark, at 6 centimeter mark, at 9 centimeter mark, now the variation of liquid pressure with the direction taken in the liquid, and the direction is to the left. So note that the probe is bent to the left and at 0 centimeter mark position. Always remember, you can pause the video if you need more time for reading the column of water in the manometer. Now at 0 centimeter mark, at 3 centimeter mark, at 6 centimeter mark, and at 9 centimeter mark. Now part C, variation of liquid pressure with density. So this time we'll be using kerosene. So take note of the probe that it is upside down and its position first at 0 centimeter mark. Now at 0 centimeter mark, read and record the height of the column of water in this expanded view. At 3 centimeter mark, always remember, you may pause the video if you need more time for reading. At 6 centimeter mark, at 9 centimeter mark, now let's replace the kerosene with glycerin. The same position and direction of the probe. At 0 centimeter mark, at 3 centimeter mark. Remember, you may pause this video if you need more time for reading. At 6 centimeter mark. Now read and record the height of the column of water, OQ and OP. At 9 centimeter mark. So for part D, the variation of liquid pressure with cross-sectional area, this time we'll be using the bigger cross-section. Okay, note that the probe is again upside down and its position first at 0 centimeter mark. Read and record OQ and OP on the table designated for this part of the experiment. At 3 centimeter mark. Remember, you may pause the video if you need more time for reading. At 6 centimeter mark. And at 9 centimeter mark. Make sure that you have read and record properly the height of the column of fluid in the closed arm and in the open arm. Make sure that you have not changed the record for OQ and OP. For the data and result, okay, this shows where you have to record all your observations and reading of measurements. So for the initial reading, now for the first part, variation of liquid pressure with depth, with the probe down. So this is the table to use. Remember to construct an OP minus OQ versus depth graph using the values in table A. Describe the graph and discuss the relationship between liquid pressure and depth as indicated by it. You are provided with graphing paper on your activity sheets. For part B, variation of liquid pressure with direction taken in the liquid. You're going to use this table. Take note that you have to copy the measures on table A and then record the position or the height of the column of fluid for the direction to the right and to the left. Construct an OP minus OQ versus direction graph at a particular depth using the tables in table B. Describe the graph and discuss the relationship between liquid pressure and direction taken the liquid at the same depth as shown by the graph. So in this part of the experiment, you are going to draw a bar graph for the depth 6 centimeter. Data and results. For part C of the experiment, variation of liquid pressure with density. So using this table, note that you have to copy the data from table A for 0, 3, 6, and 9 centimeter depth. and then record for kerosene and glycerin. On one scale, construct an OP minus OQ versus depth graph for the different kinds of liquid. How do the steepness of the graph compare? So here you're going to draw a line graph for each liquid. At one particular depth, construct an OP minus OQ versus depth density graph using the values in table C. What relationship between liquid pressure and density does the graph indicate? So here you're going to draw a bar graph for each liquid. Part D, variation of liquid pressure with cross-section. So you use this table. You have to copy the data from table A and record the data for the big cross-section container. And construct an OP minus OQ versus container area graph at various depths. What relationship between liquid pressure and container size does the graph indicate? For additional instructions for this experiment, record data, initial height of closed and open arms, and height of closed and open arms of the manometer for each setting on the table in the activity sheets provided. Compute the difference in the height of open and closed arms of the manometer. Show the computations. Draw the graphs required properly and interpret its graph. Answer data analysis, conclusions, and questions provided. Complete the report and submit to your instructor and professor. Before this video lesson or virtual experiment ends, the author recognizes the entire physics department. The video clips integrated in this presentation were cropped from the videos recorded by the following faculty: Professor Nelson Abana, Professor Danilo Olete, and Professor Richard L. Muri. The author hopes that the objectives of the experiment were met and the need to continue the teaching and learning process despite of the unfavorable situation was satisfied. Your participation in the conduct of this virtual experiment was appreciated. Thank you for watching this video. If you find this video interesting, learn the topic by watching this video and believe that other students will also learn from this video. Like and share this video. If you are new to this channel or have not subscribed to this channel, please do it now. Click the subscribe button so you will be notified of the upcoming videos. Thank you very much. God bless, keep safe, and good luck.